Hello, welcome to our channel again. Suraj here, and today I'm going to discuss about the black body radiation. So this is the topic which I should discuss before discussing about the Schrödinger wave equation because this topic is the beginning of the quantum physics. But unfortunately, I directly started the Schrödinger wave equations, expectation value, and all that things. But now it's time to really deep dive into the topic of the black body radiation, that how the black-body radiation emerges and ignites the fire of the quantum physics, and how the concept of quanta emerge from the black-body radiation, which leads to the photoelectric effect and which directly leads to the quantum physics, Schrödinger wave equations, and all of the dynamics of the quantum physics. And if you want to learn more about the quantum physics, like the Schrödinger wave equation, expectation value, what are operators, spin states, what is Pauli exclusion principle, proof of the Pauli exclusion principle, and all that things, then there is a playlist of mine on the quantum physics, and you can check out that particular playlist where I've discussed about not, I think, 5 to 6 lectures are there on the quantum physics. And if you like, you can watch that particular video. But for now, we are going to discuss about the blackbody radiation. So before discussing about this topic, the book that I'm following for this particular blackbody radiation and the statistical physics is this heat thermodynamics and statistical physics by S. Chand. So this is the particular book which is my reference book as to study these types of the topics. Language is quite hard, but pretty good book you can learn from this book. There's various types of the questions which I like the most. There are very types of the solved questions also. Unsolved questions are very less, but in some topics, the unsolved questions are quite large. But yes, quite good book you can use as a reference book for learning the black-body radiation and statistical physics or thermodynamics. Thermodynamics, yes, thermodynamics is in this particular book, thermodynamics is a very elaborate manner. So if you want to learn deeply about the thermodynamics, like that, if you have studied what's the thermodynamics in the class 11th, but want more intuition behind thermodynamics, you can check out this particular book. It's not 11th level, it's quite high to the 11th level of the thermodynamics. So it's only for the students which are regularly wanted to know more about the thermodynamics. Okay, so now let's start for today's topic of the black body radiation. So first of all, we have to understand that what exactly is the black body. Okay, this particular term, black body, and then to understand that what actually is the radiation. Okay, so black body. So generally you can think that black body is a substance, is a thing which absorbs all of the light radiation. It means suppose that is a sphere. Okay, so the light waves are coming here. Light waves are coming. Light waves of different wavelengths, of different frequencies. The light waves are coming, and what it does, it just absorbs all of the things. It means it will not reflect it. This is not the idea of the black body. It will not reflect any of the radiation that falls on it. It just absorbs it, all of the particular radiation. And that's why we call black body, as you can say that, a very good absorber of the light. But black body, perfectly black body, is quite a is not in a realistic way, because there is no object which is a perfect black body in our world. That's why we imagine an hypothetical black body. Hypothetical black body, which means in our world, if I remember, there are the black body which are very close to the 100%, but is still not 100% of the light they can absorb, and that's why this is an hypothetical object. But in our case, what we are studying is that this particular black body absorbs all of the radiation, not 99, not 98. All of the particular radiation it will just absorb, and that is black body. And what is radiation? Radiation means that's obvious that if you heat any of the objects, so if you heat any of the objects, the electrons of this particular electrons present in this particular object starts oscillating. And we all know that what happened when an electron oscillate. So when an electron oscillates, it emits the electromagnetic wave. And that's in the case of the black body. If you heat a black body like particular substance, so it will emit the different types of the radiation, and that is called the black body radiation. And that's what we are going to study, that how we can just emerge in mathematics concept. It means how we can emerge a mathematical tool so that we can understand that how energy density as per the wavelength is emitted, by a particular black body, it means we want a mathematical consideration to observe that, okay, at that particular temperature, let's say 503 Kelvin, what are going to be the graph of the emissive power to the frequency and all that things. And that what exactly we are going to study in this particular video. So yeah, I'm talking about this particular graph. So I will try to explain this particular graph, but before studying this, we have to know some terms which is quite important in context of the black body radiation. I hope that you understand that what is black body and what is radiation. It starts emitting radiation, and we want us generally a law that could fit with our experimental considerations. It means in experiments, what was found is that I will try to make a diagram that what happens in the experiment. Okay, so in an easy way, okay, so this is, let's say, E lambda. What is E lambda again? So you can say that it is an intensity of the energy that is emitted by the black body per unit area, per unit time at particular wavelength. Okay, so this is E lambda. And here you can say that it will frequency. Okay. So now what I'm trying to explain is that suppose that I heat a black body. Okay, so let's imagine there is a black body A. So I heat this particular black body at temperature of, let's say, 507 Kelvin. I'm just trying to explain this. This is maybe not with the realistic experimental observations, but I'm just trying to explain you that 507 Kelvin, if I heat this particular A black body and try to figure out the graph looks like this. Okay, let me extend this. Okay, roughly, and at 507 Kelvin. Okay, what I'm trying to say here, I'm trying to say that if you heat up a black body at 507 Kelvin, so in easy way you can understand that it will emit the radiation in not only a particular frequency, it will emit radiation in all of the frequency. Yet at some frequency, you can see that the energy radiation is high, but it will emit of all of the wavelengths approximately. And that is the case in ours also, because humans are also emitting almost all of the radiation in electromagnetic spectrum. We are emitting also the visible light, also the infrared. But as you can see that in this particular graph, there is a peak, and this peak describes that what frequency light is dominating. So in our case, the frequency of light that is dominating is the infrared. It means we are emitting infrared in more amount as compared to the our other different types of the low and high frequency waves. And that's what I'm trying to explain, that if you perfectly heat a black body, it will emit all of the radiation in different wavelengths and different frequencies, not only a certain type of the frequency, not only the certain type of the wavelength. Okay, so that's the case of the perfectly black body. So now let's discuss about some of the terms. And yes, let me remind you that what's now this is the case that as we can see that when you heat a black body, it will emit almost all of the radiation at different frequencies and wavelengths. So everybody thought that, okay, why we can't use mathematics to describe all of this particular thing? So yes, and that mathematics is a different types of the law that you see, which is a Rayleigh-Jeans law, Planck radiation law. All of these laws are the law that can explain this particular experimental curve. That will explain the emissions of the different types of the radiation at different wavelengths at a particular temperature T. It means these laws, I'm trying to explain that what are the needs of this particular law. So this law are trying to just depicts what we are going in through the observations. It will see that, okay, if I heat a black body at a temperature of 507 Kelvin, so how much total amount of energy is emitted by this particular A black body and other things like that. Okay, what is the amount of the energy emitted by the black body in the wavelength, let's say 500 nanometer. If someone asks you, okay, if the black body is emitting almost all of the wavelength of light, tell me that apart from this, with all from this, how much radiation is emitted in the 500 nanometer wavelength? And you will say, oh, I don't know. Then the law came, Planck radiation law and Rayleigh-Jeans law, the law that tells us that, okay, how can I find out the energy emitted by a black body at a particular temperature at particular wavelength, 500 nanometer. If someone asks you, okay, then tell me that how can I find out the amount of radiation emitted as a black body at 600 nanometer? I know that it is emitting 500 also, 400 also, 500 also, 600 also, but I want to only know the amount of energy emitted by the black body at particular wavelength. Now tell me what is the energy emitted. So how can you tell them? So that's came the Planck radiation law and all of the Rayleigh-Jeans law that can actually tells you that how we can generally derive the particular expression for how energy emitted by the black body with the frequency and all of this particular relationship. And that is a summary of why we need law and Planck radiation law, all that things. Now discussing some of the important terms. First important term is this E lambda. This is very important. You have to understand this. Okay, so what is E lambda? So E lambda is the energy emitted by the black body. Energy, E means energy emitted by the black body per second per unit area per unit area in a certain unit wavelength range. Unit wavelength range. Okay, so what's the meaning of this? So this E lambda is like that. Okay, this is a black body. E lambda means energy emitted by this particular section of the black body in 1 second within a unit wavelength range. It means we can say that how much of the energy is emitted per unit area. Let's say the numerical value can be easy. Okay, so numerical, I'm just taking any of the random numerical value. It is not the real numerical value. Maybe it will not be a good observation based data, but I'm just saying this to match and to know the concept of this particular thing so that you can understand it. Suppose that this is a unit area of 1 meter square. Okay, so the meaning of this E lambda, if I imagine a unit area of 1 meter square, is that how much energy is passing through the 1 meter square in 1 second, and the energy that is emitting in this particular 1 meter square area, and how much energy is of a particular wavelength, let's say 500 nanometer. I want this. How can I find this? Okay, so this is the E lambda. It means, okay, in 1 meter square area, in 1 second, there are the different types of the wavelengths of energy radiation that is emitting, but I only want the 500 nanometer wavelength. Sorry, 500 nanometer energy that is emitted in a particular unit area. How can I find out? You can find out using the E lambda, and that is the meaning of this particular term E lambda. I hope you understand the term E lambda, and the next term is E, capital E, capital E. And this E lambda is a name which is, I remember, emissive power, spectral emissive energy. I think it's power. Yes, spectral emissive power. Yes, this is the name of this particular. And you can see that how the name, this E lambda is remembered as spectral emissive power. It means only a particular spectrum we want, that how much amount of energy is emitted by the 500 nanometer of the light wavelength in a unit area in 1 second, and that is the spectral emissive power. And this E here, capital E, okay, so this particular capital E is regarded as not the spectral, it is the total emissive power. Okay, what is total emissive power? This is spectral and it is total. Then what's the difference between this? So in spectral, you can say that here we want only the energy radiation of a certain wavelength. But in the this particular scenario E, we want that how much amount of radiation is passing through, let's say, 1 meter square of a black body in 1 second. This is meaning of the total emissive power. Regardless of that, whatever the wavelength will be, maybe it's a 500, 600, we don't care about the 500, 600 nanometer. I want that what's the total energy just passing through this particular 1 meter square in 1 second, regardless of the wavelength. It means it's include all of the wavelength, 500, 600, 700, 800, whatever this is, it includes all of this particular thing. And that's the total emissive power, or capital E. Okay, so these are some of the terms that you should understand while understanding the meaning of this particular term of E lambda and the capital E. And in this particular video, we talked about the blackbody radiation, but I haven't discussed much about this particular graph because you will understand this particular graph much more better in the next video where I'll discuss about the Rayleigh-Jeans law, because these things are required to understand the Rayleigh-Jeans law. But I will try to explain this graph now in a very short and comprehensive manner, that the meaning of this graph is that what's classical and the quantum's perspective, how it differs between the classicals and the quantum's perspective. So you can think on your own that in classical physics, in classical physics, if you increase the frequency, with increasing frequency, there is an increase in the E lambda. It means you can generally say that increase in the energy, increasing the frequency, but that is not the case in the experimental, because here this yellow experimental curve is also the yellow curve is the quantum curve also, but also the experimental curve. It means what experiments, if we done the experiments on a black body, and if we try to measure the electromagnetic spectrum of a black body, the curve should look like this, but the classical physics graph look like this. It means at a certain time, if at a certain point, if the frequency increases, the graph should have to be down slope. But here it's increasing and increasing and increasing and increasing, and that does not fit with the experimental curves. And that's the problem with the classical physics, and this problem is called the ultraviolet catastrophe. Because at after certain frequency of increasing frequency, the graph should look like this downslope. But in classical physics, it is just increasing and increasing. It's directly proportional to the frequency, energy, and it's increasing and increasing and increasing. But the experimental curves are predicting something very different. But you can see that here at a low frequency, the graph of the quantum and the classical observations, classical, sorry, or not observation, classical and the quantum is exactly same. It means the Rayleigh-Jeans law, which is a classical law for the radiation law, which we will discuss in the next video, is quite good for low frequency, but for high frequency, it breaks down. So this is my video on the Planck radiation law, and I hope you understand all of these particular things. In next video, we are going to discuss about the Wien's displacement law and Stephen Boltzmann law also, which is very important before understanding the Rayleigh-Jeans law. And finally, third video is for the Planck radiation law. And in this particular video, I will going to discuss about the concept of quanta, how the quanta shape the quantum physics. Quite interesting. Yes. Okay. So hope that you understand all the things. And if you have any doubt regarding this particular topic, and if I have done any type of mistake while teaching, you can write in the comment section. And if you understand it completely, I will glad if you write in the comment section that you understand it perfectly. And if any type of improvement I needed, I will here you can comment down in the sections, and I will try to improve all of my lectures and all that things. So for now, thank you for watching my video.